This is problem 14.5. It's on page 598. A gun of mass 40 megagrams is designed to fire a 200 kilogram shell with an initial velocity of 600 meters per second. Determine the average force required to hold the gun motionless if the shell leaves the gun 25 milliseconds after being fired. Okay, so we're given a few things. The mass of the gun is 40,000 kilograms. That's the same thing as 40 megagrams. The mass of the shell that's being fired is 200 kilograms. The final velocity of the shell is 600 meters per second, and the amount of time that it takes to fire the gun, or for the shell to exit the barrel, is 0.025 seconds. That's 25 milliseconds. Now we're supposed to find the average force required to hold the gun motionless. Average force on gun. So let's begin with a free body diagram and analyze the forces acting on the gun. So we'll just draw the gun barrel in cross section, make it kind of look like a cannon, I suppose. I don't know what this gun would look like exactly, but it's a good sized gun. So basically there's force from the ground on the gun, and then since the shell is in the gun being propelled, what's propelling the gun? Well, expanding gunpowder or explosive or whatever it is. So there's gunpowder at a high temperature, and so it's bouncing around like crazy in here, pushing the shell out of the barrel, bouncing off the shell essentially. And so, but considering the forces on the barrel itself, there's a force from the shell onto the barrel, and it's the equal and opposite force onto the shell that causes the shell to come out of the barrel at high velocity. So really the body we should be analyzing is the shell, because if the gun is to be held motionless, then the force from the ground must be equal and opposite to the force from the shell. Now you see a gun this size, they do not sit still. The reason is because these are very high forces, and it's, the ground's going to give to some extent. Anyway, so I'm going to use the shell as the body to analyze, even though the force I'm interested in is the force from the ground onto the barrel, because I know it'll be equal and opposite to the force on the shell. So the mass of the shell times the initial velocity of the shell is the initial momentum of the shell, plus the force on the shell that acts over time, over that 25 milliseconds of time. That's equal to the final momentum of the shell, which is the mass of the shell times its final velocity. Now obviously the shell is not moving in the barrel initially, so its initial momentum is 0. But after the explosive is lit, then there will be a very high force acting on the shell for a very short period of time, we know that time, and that'll give rise to the final momentum of the shell. Now solving for the force, this force could come out if we're supposed to solve for an average force. Solving for that force, it would be equal to the mass of the shell times the final velocity. Now let's be careful with our signs this time. There should be a negative sign here, divided by dt. Now the reason for the negative sign is that the final velocity of the shell will be in this direction, but the force, let's see, let me make sure I get this right. No, I'm sorry, they would be in the same direction, because the average force on the shell will be to the right and the final velocity of the shell will be to the right, so I don't need a negative sign after all. Anyway, so the mass of the shell is 200 kilograms, the final velocity is 600 meters per second, and then finally the amount of time is 0.025 seconds. So notice the seconds go away. I'm making a lot of mistakes today. They don't go away. They're both in the denominator. We'll end up with kilograms meters per second squared. And what is a kilogram meter per second squared? What is this unit when we put it all together? Well, that's just Newton. So we can get rid of all those in favor of newtons. Plug this into your calculator, and it's 4,800,000 newtons, or kilonewtons, which is a a very high force. Now, let's see. So basically, this is the average force acting on the shell to get the shell to exit the gun and accelerate to that final velocity of 600 meters per second in 25 milliseconds. So the force from the acting from the ground onto the gun barrel must be equal and opposite to this force acting on the shell. From the shell onto the gun barrel is equal and opposite. And so it's just, well, 4.8 million newtons.